All right, so next up we got cyclobutane. Skeletal structure will look just like a square. And then if you think about if it was flat, this would be 90 degrees. And then we would have an overlap of all of these hydrogens, right? We would have all of this torsional strain as well. So we've got a lot of angle strain, a lot of torsional strain. So let's see what the molecule looks like in real life. It does not occupy this flat structure. Instead, it goes into a different conformer, right? So instead of going with this flat planar structure, it instead goes with this puckered structure. And in this flat structure, these bond angles are 90 degrees, whereas this bond angle is 88 degrees. And so you can think about which one of these is closer to 109.5 degrees. It's actually the 90 degrees. So this one actually has, the one on the right has more angle strain. So why would it adopt a conformer that has more angle strain? Well, think about the other types of strain here. In this flat planar one, all of these hydrogens are eclipsed with one another. And so there's a whole lot of torsional strain. Whereas in this other structure, you can tell these hydrogens are not eclipsed with one another. So there's less or no torsional strain here. And so the increase in angle strain is beaten out by the decrease in torsional strain. And so there's not really too much you need to know about cyclobutane. It's not all that interesting. Another cool thing, though, is that it can ring flip. And we'll learn about this later on with some of our more interesting compounds. But basically, you know, these carbons can be puckered up or puckered down, and they can flip, they can interconvert from one side to the other, right? So you can go from these carbons being down to these carbons being up. And this is called a ring flip, which we'll see more of later on.